My name is Tomasz, and I'm happy to give you this presentation from Warsaw. That's where I work, at the Institute of Geophysics, Polish Academy of Sciences, and usually I spend lots of time during the year in the Arctic, dealing with air temperatures, precipitation, all the meteorological elements, and also glaciers. And this presentation will be about the mass balance of glaciers. I divided my presentation into a few parts. I'll start with information for you how to get a glacier, so what's needed to glacier to appear. Then I'll describe what is a glacier. Then I'll show you the methods of glaciology, so that's the science that measures the glaciers, and different measurements of mass balance. So we should start with the snow. I believe all of you know that there are some places on Earth where snow that is accumulating during winter doesn't melt during summer. It's in some places, some conditions are needed. Those conditions are climatic, weather, and geomorphological. Those climatic conditions are air temperature and precipitation, especially snow. Fall. Then weather, I mean meteorological elements that change during seasons. So when the temperature during summer is not high enough to melt the snow. Then there is also geomorphology, and by that I mean relief. So if there is flat surface, snow can be accumulated. Of course, on steep slopes it's not possible. And important is also exposure of the slopes. The lower topographic limit is the elevation of snow line, called also equilibrium line altitude. That's the altitude above which more snow is accumulated than melted. And it varies with in different latitudes. So it's different altitude in different latitudes, as is shown here. So average altitudes of snow line taken over large areas can be used to derive a climatic snow line. For example, close to the poles, North Pole and South Pole, this altitude is around 0 meters above sea level. In polar zones, it's 200 up to 1,000 meters above sea level. Around tropics, it's 5,000 or 6,000 meters above sea level. In temperate zone, for example, in Europe, it's around 800 to 3,200 meters. And near the equator, due to higher precipitation, it's between 4,500 and 5,000 meters above sea level. And having that conditions in different parts of the world, there are glaciers and ice sheets. This map shows the recent glaciation. So as you can see, there are huge two ice sheets. One is the Antarctic around the South Pole, and there's also a huge ice sheet in Greenland, the biggest island in the world, in the north, here in upper right side. And of course, high mountains also can have glaciers, depending on the conditions that were mentioned before. So for example, Himalayas, Cordilleras, Andes, and also Pyrenees and Alps in Europe, for example. What's happening with the snow? It falls as a light snowflake and then crystallizes from atmospheric moisture and falls as a snow on the Earth. Then it's accumulated, so snow crystals become more and more compacted. Maybe some of you made a snowball, so it needed compaction of the snow. So the air was forced out of pack and the density increased. And in some places where this snow can accumulate, if there's enough snow, glaciers can form. This chart shows transformation of snowflake into glacier ice. Between there is granular snow and firn. And as I mentioned, it means higher density. So here we have a table with snow and ice densities. So for example, really fresh new snow that falls during the calm conditions can weigh up to 70 kilograms per cubic meter. Damp new snow is between 100 and 200 kilograms per cubic meter. Settled snow, which is older snow, is between 200 and 300. When there is wind, it can also pack the snow. So between 350 and 400, there is wind-packed snow. Firn is between 400 kilograms up to 830. And very wet snow and firn is 700 up to 800 kilograms per cubic meter. And then there is glacier ice with huge compaction. The mass and density is 830 up to 917 kilograms per cubic meter. So this conversion of snow, of the snowflakes, to glacier ice can take many years, of course. When enough snow is accumulated and ice appears, it moves down slope under its weight. And there's also this pressure from above of the overlying snow and ice. And that's how the glaciers appear. And the shortest definition of the glacier that I found, glacier is a mass of ice continuously moving from higher to lower ground. Maybe it can be seen in this picture, how the glacier moves down. And of course, on pictures, those glaciers look motionless, but they really move. And their mass movement is one of the most powerful forces shaping the Earth's surface. And this glacier ice movement, together with the transported material, destroys whatever is on its way. So it erodes slopes of valleys, reshape existing landforms, move and accumulate material on sites and at the bottom and in the forehead of glaciers. Here, as you can see, is the left side of the glacier. It moves some materials on the side. That's the picture of the material underneath the glacier. The glacier moves from the right to the left, and as you can see, it squeezes and pushes the materials underneath. And there's also material inside the glacier, because it's not only snow inside the glacier. There are also avalanches, and all the materials that are pushed are also pushed together with the ice. Also, on top of the glacier, you can find sometimes huge blocks of rock. So here, for example, is my friend standing under the huge rock on the left. That's for the scale. Okay, so when we have glacier, it was moving forward and then moved back, because the climatic conditions, when it's colder, a glacier moves forward, and when it's warmer, it melts, so it moves back. The pushed material that was in the front of the glacier stays as terminal moraine. The materials on sides are lateral moraines. And when it moved back, all the material that was inside the glacier and on the top of it stays as ground moraine. All the materials, especially sand and till that was washed out from the glacier in the front, accumulates as cinder. So, as you can, as I said, moraines are materials deposited by glacier. Here we have example of ground moraine. Please put your attention into this part of the picture. There is darker and brighter rock. Yeah, and here, that's this part of the picture. There's my friend here for the scale. Because in these areas, there are no trees, no buildings usually, so it's hard to see the scale of these processes. But you have to know that glaciers are really strong, and they can move huge blocks of rocks. In the 19th century, some artists had a vision, and in his opinion, the glacier looked like a dragon. And when you go to the field, you can see some glaciers. For example, this one in Alaska. Maybe some of you can see dragon as well. Even in close to each other valleys, the glaciers can have different sizes, shapes, and they really depend on local conditions. they depend on accumulation and ablation. So what is accumulation? Snow and ice from direct snowfall, blown snow, and avalanching from slopes above, because there are mountains around the glaciers, so there can be avalanches. And they are collectively termed accumulation. That's the added material, accumulation of ice and snow on the glacier. Then there is also ablation. So during winter, snow accumulates. During summer, there is ablation, so melting, sublimation, or calving. All of those three are ablation. That's the example of melting on this picture. Higher temperatures melt the ice. Sublimation, that's the transition of ice into vapor. I guess all of you know this chart. And there's also calving. Calving is the breakaway of ice blocks when the glacier terminates in the sea. Huge blocks of ice fall down from the glacier from the front, and they float away as icebergs. And that's the natural phenomena when the glacier meets the sea. Here we can see the big glacier with positive mass balance. So the amount of snow accumulated during winter was larger than the amount of melted snow during summer. When the mass balance is positive, the glacier increases in volume. On the other hand, there are glaciers with negative mass balance. Of course, it can be different in different years. So when the mass balance is negative, the snow melts from the snow from previous years can melt, and also the ice can melt. So the glacier retreats, moves back. Here's the example. In this part, above the equilibrium line altitude, so the snow line, there is snow that accumulated during winter. This picture was taken in September. So after the summer, some snow was left in upper parts of the glacier. And there's below the equilibrium line altitude, there's ablation zone. So in this part, more ice was melted, and all the snow was also melted from the previous winter. And of course, it depends on different glaciers, different locations, different exposures. So this line, this altitude can look different even in close valleys. Here is the other example. Two glaciers located next to each other, but the altitude of the snow line is not, it's never a straight line. The gain and the loss of ice over time in glacier systems is known as the mass balance. Here we have the equation. So what is mass balance? Annual balance is annual accumulation plus ablation. That's the easiest way to translate this equation. So when we have annual ablation, so AA is annual ablation, CA is annual accumulation. When we add these two, we have the annual balance, so the net balance, also called. On this chart, you can see the accumulation zone, the ablation zone, and there is also glacial budget in the table. So when the accumulation is lower than ablation, we have negative mass balance. It can be also equal, accumulation and ablation, so the glacier didn't change, the mass balance is the same. And there can be also accumulation higher than ablation, so we have then a positive mass balance. And as I mentioned, on the same glacier, also in different years, it can be different. So here we have Svalbard in Svalbard in the autumn of 2008 in the upper part, upper right side. We can see the ablation zone really small, and on the other one really huge. Almost whole glacier was in the ablation zone. So we can see the mass balance, which was positive in the upper part in 2008 and negative in 2014. All those measurements taken on the glaciers by scientists are the study of glaciology. That's the science dealing with the study of glaciers. And recently we have advances in technology, and there's also ability to reach remote places on Earth. So it allows better recognition of polar and mountain areas where glaciers form. That's why many scientists from around the world are dealing with glaciers. To determine the mass balance of snowpack on the glacier, scientists measure the depth of it, and they also measure the water equivalent. So, for example, in Svalbard, there is Hans Glacier close to Polish Polar Station, and there we have net of ablation stakes. I can show you how these stakes look like. So there is a stake put into the borehole on the glacier, and when we measure that, we can check how much snow was accumulated when we go there in the spring, and then how much snow and ice was melted in after the summer. And here we have, there's my friend in the snow pit. He measures the density of snow in this whole column. That's what we do during spring and in early autumn. So in late winter or in spring, we have this ablation stake, which is above the snowpack. So HW denotes ablation stake above the snow. DW is winter snow depth. Then we have winter snow density that is measured in the snow pits, as was shown in the picture before. And in the late summer, in accumulation area, we have also some snow that's left from previous winter, so we can measure the stake above it. And in ablation area, we check how much snow and ice was melted. Other charts shows, yeah, as you can see, the ablation stake drilled in the ice in autumn. Then in early winter, snow starts to accumulate, and then there is maximum of accumulation in the end of winter. Then during spring, it starts to melt. During summer, in the ablation zone, all snow and even some ice can be melted, so you can see the difference between winter balance, summer balance, and addition of them is called net balance or annual balance. There are different units of mass balance. We usually use in the publications water equivalent, which is in meters or millimeters of water. It says how much water can be melted from given thickness or volume of snow or ice. So for example, when you have 1 meter of ice, 0.9 meter is water equivalent, because the density of ice per density of water is 0.9. When we have 1 meter of snow, it can be, if it's fresh, it's around, as it was mentioned before, around 200 kilograms per cubic meter. So 20 centimeters or 0.2 meter of water equivalent is in this snow. Other units are mass in kilograms or gigatons. When we deal with huge ice sheets, we always say about gigatons, not the millimeters. And there's also other unit called sea level equivalent. So for example, when 100 gigatons of ice melt, it's the addition of 0.28 millimeters to the sea level. As I said, mass balance is expressed in millimeters, meters, sometimes centimeters. So yeah, again, 10 centimeters of snow with density of 100 kilograms per cubic meter gives 1 centimeter of snow water equivalent, and 10 centimeters of ice with density 900 per cubic meter gives 9 centimeters of water equivalent. So there is more water in ice than in the same layer of snow. So what we do is measuring the stake, as I mentioned. For example, here we have September 2015, so the end of ablation season. So the ice here has density of 900 kilograms per cubic meter. In the middle, we have the end of accumulation season. So we measure in the snow pit, and also we measure the stake that is above the ice from previous year. So 70 centimeters of snow with the mass of 400, with the density 400 kilograms per cubic meter. So we can check at the end of the year, so I mean the end of ablation season, how much snow and ice was melted. So for example, when we measure the stake that was 1 meter above the ice in the previous year, and now it's 1.5 meters above the surface of ice, we can know that it's ablation zone. So how much snow and ice was melted? It's easy calculation. As you can see, snow water equivalent is 0.4. So winter balance is 70 centimeters multiplied by 0.4, so it gives 0.28 of water equivalent, 0.28 meters. Then summer balance is, of course, net balance and winter balance minus winter balance. So when we calculate the annual balance, which was 1 meter minus 1.5 multiplied by 0.9, it gives 0.45 meters of water equivalent. So summer balance was minus 0.73 meter of water equivalent. There is similar example for you to calculate the mass balance given in homework that was sent to you, and I hope you will feel this. You will calculate what's the mass balance. So we have those direct measurements of ablation stakes. From this, we obtain the mass balance at different points of the glacier surface because we have this net of ablation stakes. And to get the whole glacier mass balance, we need to interpolate all those ablation stakes and measurements. So yeah, we have this net of ablation stakes in different parts. That's how they look. We measure that. And on the upper left, we have winter balance. On the lower left, we have summer balance. So from that, we can calculate the net balance or annual balance of the glacier. And that's something that is done around the world. There is World Glacier Monitoring Service. So different glaciers are measured in the same way. And on the website of this World Glacier Monitoring Service, we can check the data from previous year. What was the mass balance in different parts of the world? What is that for? It's done because glaciers are really sensitive indicators of climate change. They constantly grow and shrink in response to changes in temperature, snowfall, and other factors as well. And that's something that I do in my job. I deal with climate changes. So my latest recently published article is about inter- and intra-annual changes in air temperature and precipitation in western Spitsbergen. Spitsbergen is located close to the pole, some 1,000 kilometers from the North Pole. It's the biggest island of Svalbard archipelago. And in Spitsbergen, in the southern parts, there is this Polish polar station that I mentioned before about it. Yeah, so in Hornsund, we have data from the 70s. So we averaged the data throughout the year. For each day, the decadal average was calculated, and here you can see the differences in the blue lines. Blue lines denote the oldest years. I mean, from 1979 till 1988, these are average temperatures for each day. And the red lines denote the recent data, so from 2005 to 2014. As you can see, there are changes of air temperature, especially in January and December. and that's of course important for glaciers. There's no big difference between temperatures in summer, but accumulation of snow and snowfall during winter and those temperatures are important for the glaciers, as you will see. So what we can see is that we have warmer climate now than it was 30 years ago. Here is the chart presenting the sum of precipitation. Now we measure the higher precipitation during August and September, which is rain, and rain melts the ice. So it's really important for glaciers because they don't gain the mass, they lose the mass. If you're interested in the data that I'm dealing with, and it's the data that is collected in Hornsund, you can Google this site, hornsundIGF.edu.pl weather. There are meteor bulletins. We prepare those every month after the month. And having this data and having some historical data, my friend was able to prepare this map. That's the map of Hornsund Fjord. Fjord is 40 kilometers long. And in the beginning of the century, of the 20th century, so 117 years ago, the glaciers extended up to the middle of the fjord. As you can see, this blue line, this yellow line shows the extension of the glaciers in the beginning of the century, of the 20th century. And now those glaciers that were so huge are moving back. So their extension is also in yellow, but on the right side and upper sides. So they moved back some 15 kilometers. And now I would like you to focus on this particular point that appeared in the middle, in the lower part of the picture here. So that's the place where this picture was taken, on the top of Hornsund Tind. And here we can see the Hornsund Fjord. And the glaciers in the beginning of the 20th century were up to here, from the right to the red line. And now, because of the negative mass balance, they moved back. For example, Hornbren moved back 14 kilometers. Samarinbren 10 kilometers. Other glacier, Peyerbren, moved back 8 kilometers. So they had negative mass balance almost throughout the 100 years. That's why they moved back. We can look back in 100 years, but it's also nice to take older pictures from your friends and take the pictures from the same points. For example, my friend did that in 2008 and 2014. So you can see the extension of Hansbren in 2008 and 2014. You can see it moved back. But as I mentioned before, there is no scale. So here you can see the front of Hansbren, but there's something to give you the idea what's the scale of that. Here you can see in the middle glaciologists on their way to the glacier with the ablation stakes. So we can imagine what's the scale of these processes when these glaciers move back. It can be kilometers. That's a picture from 1985. And that's my picture from 2010. As you can see, this glacier moved back, retreated some 800 meters. Yeah, same. So these were glaciological methods, ablation stakes, and measurements of density of snow, so water equivalent. And here there's also a geodetic survey that can be made, so we check the elevation in different years. I see it doesn't work here, but maybe you will see in these slides. So that's the digital elevation model of the terrain. In the middle there is glacier in 1990. And after almost 20 years, you can see the differences of elevation of this glacier. So as you can see, glaciers move back, and also they have they're less thick than they used to be. Now I would like to show you a short movie about these processes. As I said, glaciers can have a positive or negative mass balance. So when they have positive mass balance, they move forward. And as I said, they just move everything what's on their way, and they reshape the Earth surface. Yeah, so that's the example. When the mass balance is positive, they can reach the sea, and then they can calve into the sea. And when the mass balance is negative, so the climate is warmer, they melt away. So they move back, and when they moved all the terrain that was ahead, and when they melt, the sea level also rises. Those valleys that were shaped by the glacier can be flooded by the sea water, and that's how you get the fjord. One example of the fjord is Hornsund, that was shown. Yeah, positive and negative mass balance. That's the retreat of the glacier. Now I prepared some exercise for you, so hope you have pens and piece of paper. That's something that was sent to you also in email. So here we have exercise. You have to calculate the winter balance, net balance, and summer balance, having this data. So here we have first answer from Liliana and her school, I guess. Winter mass balance is 0.44 meter of water equivalent, and that's the correct answer. Bravo. All right, so if there's no other questions, yeah, I prepared some literature for you if you are interested at the end of the presentation, because I had 40 minutes for you, and of course there's a lot of books about the glaciers, about the mass balance of glaciers. Here are examples in English and in Polish, and I believe you can find books in your languages as well.